everyone. Today video is based on metallurgic aspect of rotary instrumentation. I felt to take this topic out of curiosity to know like files are made up of what metals, and during the even SR exams various questions are based on this. The biggest nightmare for clinician was instrument separation during root canal procedure. It was, but now we have many. In this phase of COVID-19, nightmare of aerosol contamination, wearing of PPE suits during the procedures. So the protocol for the treatment has changed. So the cases which are indicated for root canal treatment and not contraindicated for single visit endodontics can be done in a single visit successfully using the best armamentarium, and we can't dare to commit any procedural error. The metallurgy of specific material should be understood to achieve the optimum property for application. Why such a paradigm shift occurs from from stainless steel to NiTi? Because the stainless steel instruments were very rigid, they have low cyclic fatigue resistance, they cause more procedural errors like canal transportation, and they cause ledge formation. And we cannot pre-bend the stainless steel files. So they lead to more errors during the preparation. But the stainless steel files, they maintain their cutting surface. They maintain their sharp, long-lasting cutting surface for a long time. They have excellent manipulation control. They provide us with a tactile sensation that is not provided by nickel titanium system. The inherent weakness of NiTi system is they fracture without warning. And the young modulus, that is the hardness of the stainless steel file, is very large, that is around 193 gigapascal in comparison to NiTi file, whereas the young modulus, that is the hardness, is 48 gigapascal, means they are more flexible. Now, why the file fracture? File fracture in a canal because of two things, either because of cyclic fatigue or torsional stresses. When a file gets rotated into the canal which is curved, it is subjected to continuous compression and tension inside and outside of a wall that lead to fracture of an instrument. So to remove that cyclic fatigue, we need to have a file which is more flexible. And for the torsion stress means it occurs when a file, two parts of the file, they rotate at different speed. Like in a case of narrow constricted canal, tip of the file is get engaged in the apical part and shaft continue to rotate at another speed at comparison to the apical part. So the file get fractured because of rotational stresses. So to overcome that torsional stresses, file need to be more rigid. So we need to have a file which is more flexible also to have good cyclic fatigue resistance, and it need to be more strong also to overcome the torsional stresses. So since the NiTi was introduced in 1980, it has continued to revolutionize the field of endodontic instrument. We have plethora of file systems in the market which are based on different alloys. Like we have conventional NiTi alloy. We were having on that system, we have M2 one shape ProTaper universal. On the basis of R phase, we have twisted file adaptive K3XS, K3XF. M wire technology, we have reciproc, wave one, CM wire, gold and blue heat treated wire, max wire technology, T wire technology. We are going to discuss all the systems in detail now, all the metallurgical alloys. Now, why this NiTi, it is different, why it is an exotic alloy that stand out from other alloys? Because of two properties, because of super elasticity and because of shape memory. And during these phases, it is interconversion of two phases, that is austenite and martensitic phase. And what is martensite transformation? So a metal which is a NiTi raw metal, low alloy, is in the form of parent phase. Parent phase is in austenite phase, which is cubic structure having BCC structure, body centered. Now, when a shear stress get applied on it, it get changed into the structure. It get show twinning, because whenever a stress occur on the shape memory alloys, either they slip along the grains, either they show slipping or they show twinning. So in this niti, the martensite phase, it showed twinning of the grains. So we have two martensite phase, like the twinned martensite phase and the deformed martensite phase. So now what is superelasticity? Okay, we know that there is a term superelasticity, there is a shape memory. Now what is actually superelasticity? Superelasticity is the recovering the original shape after large deformation induced by the mechanical load. So the original shape that we get after deformation is called as superelasticity, and we can have a complete recovery of deformation up to 8% strain due to phase transformation between austenite and martensite. Transformation is between which phases? Phase transformation is between the stable austenite phase, that is the parent phase, and the stress induced martensite phase. So there is an interconversion of phases from austenite to martensite that lead to this phase conversion and lead to accumulation of the stresses up to 8% that is not seen in with other alloys. What is shape memory then? Shape memory, maintaining a deformed shape up to heat induced recovery of original shape. But we can maintain a deformed shape up to a long phase until we provide a heat treatment to it. This deformed phase we can achieve to this martensite phase. What is martensite transformation then? Martensite transformation, it is diffusionless. Here it is diffusionless phase transformation in solid in which atoms they move cooperatively. In this atoms they move cooperatively and often by shear like mechanism. When a shear like force get over that phase, it moves cooperatively without giving a gross change in the structure. That is called martensite transformation. So all the companies, they are interplaying, all the manufacturers, why they are making so much file systems. It is the interplay between conversion from austenite to martensite, at what temperature martensite is converting to austenite is converted to martensite phase. So this is a simple diagram explaining this structure. This is the parent phase, which is in the form of austenite in BCC structure. Stress get accumulated on it, we applied the stress, it goes stress induced martensite transformation. The martensite, it goes unstable, it become unstable. There is cooperative change by the shear stress, they change in the structure, and when we unload it spring back to original state. This is basically a superelasticity property is because of austenite phase. Now shape memory effect is because of martensite. When a alloy is subjected to cooling, like when it is heated and when it is cooled, the twinned martensite that I told, when a stress is applied on a martensite phase or a shape memory alloy, it either go twinning or slipping. Here the niti alloy goes twinning. It is deformed, it is twinned martensite. Here the molecules are arranged in various directions, and when I apply more stress, it becomes stable. That is the deformed martensite. And on heating, it get again converted to austenite because the martensite phase is highly unstable. It is unstable, it cannot stay at room temperature for long. It has to be converted to austenite. And why we want a file to get converted to austenite phase? Because the austenite phase is very hard, it is rigid phase, it is not as flexible as martensite. Austenite phase we want at room temperature, and martensite phase we want in when we put a file into the canal. So there are various transformation temperature. Austenite starting phase, austenite finish, martensite start phase, and martensite finish temperature. So when a alloy or niti alloy is heated, it started to convert from austenite start temperature to austenite finish temperature, and when we start cooling, martensite start get converted completed till martensite finish phase. Above that martensite temperature of this austenite finish temperature, it is stable. Austenite phase is non-elastic and it is very hard. Martensite phase is low temperature phase, it is a low temperature phase, it is asymmetric. It is asymmetric and it occur at low temperature. Austenite phase, it occur at high temperature and it is stable phase. The Young modulus, if we see for austenite, it is rigid as I told, so it has 80 to 90 gigapascal of Young modulus, and Young modulus for martensite phase is 30 to 40 gigapascal. Now this is the phase transformation diagram for NiTi. Now what in nearly equiatomic NiTi? Nearly equiatomic means around 50% of nickel and titanium. Mainly we have more than 50% of nickel. So the phase transformation in NiTi, it occurs because of thermomechanical process. That is the thermoelastic transformation. From austenite to martensite, austenite is in BCC structure. It gets converted to monoclinic stage, which is martensite phase. And this phenomena is sensitive to this conversion from austenite to martensite. It is sensitive to the fine structure of parent phase, beta phase that we call, like how much we have in the raw material, how much we have amount of nickel. If I increase the amount of nickel, it will change the transformation temperature of austenite and martensite. We may have an early martensite phase. Or the aging process. What is aging process? When we subject a metal and we subject an alloy to repetitive heating and cooling cycle, it remove its stresses, inherent stresses, and become more flexible. Or third is called as thermomechanical treatment. And fourth is addition of alloy. If we add some new alloy or a new metal to NiTi, like if we add some iron to it or some copper, it shows the change in properties. It affects the structure and it will improve the memory behavior of an alloy. This is the twin martensite phase. It's subjected to stress. This is the twin martensite state. Here the deformed state, grains are arranged in deformed state. When we apply a stress, continuous stress, it shows a proportional change. As the stress are increasing, strain is increasing. But after a particular time, the amount of stress is the same. It is maintaining, it is regaining, accumulating the strain, irrespective of increase in stress. This is martensite reorientation. When a martensite phase, it get converted from twinned to deformed martensite. This it is called as martensite reorientation. Accumulation of the strain in NiTi occur by two phases, either by martensite reorientation or stress-induced martensite conversion. Stress-induced martensite conversion, it occurs when a stress is applied to austenite phase and it gets converted to martensite either by application of temperature or either by application of the stress. But here the martensite reorientation, it occurs in between the structure. Molecules change their shape. And during the martensite reorientation, that is conversion of the twinned martensite to deformed martensite, which is more regular, it is able to undergo plastic transformation. Plastically, it can deform, but without fracture. And then it came down to normal structure and then we again heat it. When we again heat it, this alloy, it will again its normal shape to austenite. So to gain the austenite phase, we need to heat that alloy. And to gain a martensite phase, we need to cool. At what temperature, at what phase we are able to take this martensite phase, it will tell the properties of a file. If a file has more martensite phase, it is more flexible. If a file has more of austenite phase, it is more rigid because it has more Young modulus. It is more rigid. So inside the curved canals, we want a file which has more of martensite phase. So I can change the martensite start temperature. I can have this narrow graph that I can have the martensite start temperature just after austenite finish temperature, as we have seen in the last, like if this is a narrow graph, like just after austenite finish temperature, I can have a martensite start temperature, and in cooling we can have this flexible phase, and when again I heat, it will regain its normal shape to austenite phase, which is hard and rigid. Now we will be discussing different types of alloy and what are the file system which are based on different type of alloys. Conventional NiTi alloy. Conventional NiTi alloy has around 56 weight% of nickel and 48 weight% of titanium. Austenite finish temperature is below body temperature. It means austenite finish is below body temperature. It means it has mainly of austenite phase, because in the body temperature of around 30 to 37 degrees Celsius, we are applying a stress, but austenite phase is finishing before the body temperature, means mainly of austenite phase it consists of. And we already discussed austenite phase is very rigid, it is not flexible, it is rigid file. It's going to be, we cannot twist this file, we have to grind this file. So in the manufacturing of the file process, we have two things: either we can grind a file or we can twist a file. Alloy which is very flexible, we can twist it, but which is not flexible, which is an austenite phase, we have to grind this file. So it has been seen during the manufacturing procedure, because it's a contact grinding procedure, we are subjecting the file to micro fracture on the surface. And during the, when we use these files during the preparation of the canal, during biomechanical or cleaning and the shaping of the canal, the fracture, it get accumulate, the fractures or the stresses, it get accumulate on these micro crack or fracture lines and lead to spreading of that fracture line and ultimately leading to fracture. So to overcome this problem, we start to electroplate the files. How we start? We start electroplating the files. What is electroplating? Electroplating what is electroplating is to establish the final surface finished, achieve the smooth surface for the or to remove the surface material to make it more smooth. We just, electroplate is just a procedure to remove some surface defect so that it is more smoother. Now, like in cases of conventional nitrile alloy which is electroplated, we have biorays and I-rays. Other files which are based on conventional nitrile alloy, we have one like M2, we have one shape system. Means these one shape and M2 file system, they are based on austenite phase. If they are based on austenite phase, means they are more rigid. They can be used in a canal which is straight or slightly curved, not in highly curved or angular canal. So then we come to M-wire technology. There is also two school of thoughts I forgot to tell in about electroplating. Like in electroplating, there are two school of thoughts. Like some are saying, like if file is electroplated, there won't be any micro fractures, there is an increase in resistance to fracture. But some study, they shows that electroplated file also, they show fracture pattern. It is in a zigzag track pattern. It is a SEM study, scanning electromicroscopic study, which shows that they also show fine irregular pattern which is in the zigzag pattern, comparative to non-polished file which show the crack along the machining grooves. It is a study done by Lopes et al. In 2010. Now coming to M-wire technology. M-wire technology, what it consisting of? It consisting of austenite phase with a small amount of R phase and M martensite phase. Because it has austenite phase and martensitic phase and a small amount of R phase. I'll be discussing R phase later. What are the file systems which are based on M-wire technology? In 2007, the Sports Wire USA has developed this. It is basically a technology, it is basically a thermomechanical treatment to develop an alloy which is more flexible than conventional nitrile alloy. So we subject an alloy to a special treatment that lead to the file that is more flexible and able to have a more cyclic fatigue resistance than normal files. So in this system, we have reciproc, we have wave 1 and we have protaper next. Now discussing this file technology. Now how this file are manufactured? We take around 55% of nickel, around 44.2% of titanium, some amount of trace elements. I have told you this transformation temperature interconversion from austenite to martensite phase, it is get affected when we add some tertiary or third alloy or third metal to it. So some amount of trace element less than 1% being added to this to alter the transformation temperature. Its austenite finish temperature is 43 to 50 degrees Celsius. Means it is above the body temperature. The conventional nitrile alloy austenite finish temperature is below the body temperature. If it is above the body temperature, means austenite phase is not only, the phase in this is not only austenite, means it has some another phase, like it has martensite phase and R phase. Because when it start from this austenite start to austenite finish, it is not coming at body temperature. It take a time around 40-50 degrees Celsius when it is subjected. In between, it is interconverting. It is transforming from another structures, which are M and R phase. At body temperature, it has. So if it has M and R phase, I already told martensite phase is very flexible. Its Young modulus is less than austenite. It is going to be more flexible than austenite phase. So it maintains super elasticity. It is more flexible and it has a unique graph pattern. Means it is not following that proportional rule. Stress is equal to proportional to strain. It is undergoing a yield phenomena. This yield phenomena, then it is showing the stress-induced martensite transformation. I already told stress-induced martensite transformation is because of austenite is converted to martensite. But why? How this yield process occurred? Why it has taken so much stresses before converting to martensite? It means there is some another phase in between austenite and martensite, that is the R phase. We'll discussing what is R phase in the next slide. So there are two other phases in between, that is the R phase also occurring. M phase is also in this there, so it's going to be more flexible than conventional NiTi files. So it has improved fatigue resistance, and this fatigue resistance, more cyclic fatigue resistance, because of martensite reorientation. Because the files are undergoing martensite reconversion, it is able to bear more fracture resistance compared to conventional NiTi files. Okay, now in this file system we discuss like M wire. It is mainly austenite with M and R phase, but these file systems are still not that flexible that we need to have for curved canals or double curvature canals. So what these companies have done, we'll discuss it on the maybe in the next videos. Like we have also changed in kinematics. Kinematics means all the file system are not showing rotary motion. They're also showing reciprocating motion. Reciprocating motion like this reciproc and wave one, these files, they don't continuously rotate. They show reciprocating motion, these files that reciprocate in counterclockwise and clockwise motion, so that the cyclic fatigues on this file is reduced because it is not that flexible. To increase the flexibility or to reduce the fracture resistance, we have another change in the alteration. We have made another alteration, like change in kinematics, change in the motion. And the blue taper next is a file by Densply. What it shows, like it shows asymmetric, eccentric rotation. It shows a swaggering motion, snake line motion. We'll be discussing that on the next video maybe. Like we have also change in cross section in ProTaper next. So to overcome one defect, okay, this is much better than conventional NiTi, but it is not as good as other R phase or martensite phase transformation. So we have changed the motion of these file systems. Now coming to R phase. What is R phase? R phase is intermediary phase that occur during the conversion from austenite to martensite phase. So according to this is a book that is given in this is an equation. When the alloy, it goes transformation from austenite to martensite, aging at, this equation is given in a book by Otsuka and Wyman by Cambridge University. When the alloy, it get transformation or get aging, which we tell aging process at 680 degrees Celsius, it shows various phase changes. What is these? These are basically decomposition of NiTi alloy. During this decomposition of an alloy, there is an intermediate phase which is Ti3 Ni4. This is basically the R phase. What is this R phase? Which that occur in between austenite to martensite phase. With it is one of the metastatable stage. But in the metastate, it can be converted to martensite but at that particular temperature, we get an R phase. What is the property of this R phase? It is rhombohedral in structure. In this R phase, we can twist a file. We are able to twist a file because it is highly flexible. Its Young modulus even less than martensite. So in this phase, we can twist a file, and when we are twisting a file, we are not grinding a file. It means we are not inducing any microfracture on the surface, though these files are going to have improved fracture resistance compared to other file systems. K3XS, no doubt, it is manufactured in R phase, but it is an exception. It is not a twisted. Here, this file system is not twisted. It is manufactured by grinding only because it is subjected to R phase treatment after manufacturing. It is a post manufacturing treatment that is given to K3 except by Cibron endo. And now twisted file adaptive, it's a file system which is also based on R phase. And in this R phase, what we are twisting a file. It is manufactured in R phase, and we are surface special surface treatment we are like is also given to the file system to improve the flexibility of the file. And the twisted file adaptive by Cibron and only, this file system motion is also different. It shows adaptive motion. It rotate also, it reciprocate. It has an adaptive motion. When intracanal torsional forces are increased, it shows adaptive motion, and when the stresses are less, it continuously rotate. Now we can show the properties of martensite. Now what is martensitic phase? Martensite is softer, like high flex CM files. High flex CM files are manufactured in martensite. Already we have discussed martensite phase is very soft, it is very ductile, and what actually in this example we know about high flex CM file, that is very popular file by Colteen. What is the difference in this? Because it has mainly of martensite with varying amount of austenite and R phase. So if it is mainly on martensite phase, it's going to be highly flexible file. It shows pseudoplasticity and shape memory on heating, and also it shows martensite reorientation plus shape memory transformation to martensite phase. It is highly flexible. What is the difference between a file which is formed in martensite at room temperature and austenite phase? It spring back to normal shape, but it maintain its shape memory, control memory files. If I put in a curved canal, it may maintain its file and get converted to the normal shape after heating when we subject it to heat treatment. What heat treatment? Like if we autoclave a file, it comes back to its normal shape. CM file was introduced in 2010. Is the first thermomechanical treated nitrile file that does not possess superelastic properties, not at room temperature, not at body. Superelastic property means it does not show austenite to martensite conversion. So because of modified phase composition, CM wire can be deformed because of reorientation of martensite variants. It is changing its shape because of martensite reorientation, not by stress-induced martensite conversion. It is not at all converting to normal shape. It is not coming to its normal shape during unloading. It is maintaining that shape. So when a file, it maintains that shape. When you put in a canal, it is causing less procedural errors compared to other files which shows a change in normal shape after putting into that, because it has mainly a martensite reorientation, not austenite phase. Its angle of deflection is more than other file system, but when a file, it is a study done which shows like a file which shows control memory, they are subjected to lateral cut, but they have increased cyclic fatigue resistance. Increased cyclic fatigue resistance because they are better to do this cleaning and shaping in the curved canal. EDM, what is EDM? It is electric discharge machining. EDM means electric discharge machining. High-flex EDM files, this is also from Colteen. It is manufactured from special procedure. What is this special procedure? Like this is the machining tool, this is the workpiece, and this is the dielectric solution. We make them close to each other till that dielectric solution it get ionized. So when it get ionized, it lead to formation of a spark, and that spark cause the accumulation of the sum of the surface metal. So that lead to formation of these defects on the surface, and thus lead to the formation of the file. It has been said by the company manufacturers, like during this procedure we are forming a file by EDM, we are giving the surface a surface hardening. So it's going to be more harder, more torsional stresses, able to bear more torsional stresses compared to CM files, M wires, and also having more flexibility. It is also having more flexibility plus more strength compared to M wire and conventional wire technology because of surface treatment during manufacturing. They have higher range of deflection, lower because it is a higher range of deflection, able to bear more torque stresses compared to M and nitrile wires, the transformation temperature is higher than CM wire. All the transformation temperature, whether austenite start, austenite finish, martensite start, it is higher than control memory. Despite the reduced austenite phase, high flex EDM, they have harder than the conventional CM or conventional NiTi file system because of surface hardening. So compared to even control memory files, they are more harder, and even to conventional NiTi file systems. Their austenite start temperature is around 21 degrees Celsius. If the temperature is 21 degrees Celsius, means our body temperature is more than that, around 30 to 37 degrees Celsius. So we don't have any austenite phase at body temperature. It is purely a martensite phase with small amount of austenite and R phase. So it is highly flexible with surface hardening. Now we have also blue and gold heat treated. What is the difference in these heat treatment? These heat treatment are given after manufacturing. After we manufacture a file, we give a blue and gold heat treatment. Blue is the name given because on the surface the titanium rich coating is formed, and which gives a characteristic blue color. What are the file systems that occur in this is reciproc blue, ProTaper gold, V1 gold, and these file systems, they have control memory effect like high flex CM files, but the difference is that they are subjected to heat treatment during the manufacturing procedures. They are subjected to heat treatment post manufacturing treatments. So what is the best factor in these file system means they do have some austenite phase plus martensite phase and some of the R phase. So they are also rigid. They do have torsional stresses but flexible also. Their flexibility is more than M wire technology and conventional NiTi technology, and they maintain the more their preparation during the canal is not lateral cutting. They maintain more centric shaping of the canal compared to other file systems like high flex CM. They cause more lateral cutting. So these two, V1 gold and reciproc blue, they shows reciprocating motion. ProTaper gold is rotary file system. A very new two of technology is also there. One is max wire technology and another one is T wire technology. In the max wire technology, FKG Dental, they have developed a new thermomechanically treated NiTi file, which is a max wire technology. Means it convert to martensite, austenite and electroplated wire. It has both shape memory and super elastic property in clinical application. These file systems are XP Endo Shaper and XP Finisher. These file systems, they show martensite phase at room temperature and get converted to austenite phase when we are removing the file. When we are placing the file into the canal, shows martensite phase, and when we are removing, when we are taking the files, it shows austenite phase. Change to curved, exposed to intracanal temperature due to phase transformation to austenite phase, because there it shows super elasticity. It is showing super elasticity because it has austenite phase also, and during the preparation it is super elastic, and when we insert the canal into the canal, it shows shape memory because it is in room temperature, it is martensite, and when it is get converted to austenite phase when we are inserting into the canals because it is rigid, and when we are preparing a file, when we are preparing the canal, it shows super elasticity. It has low torsional stresses. That is the main drawback of this file system. It is highly flexible, low torsional stresses, but it is a very good file system. And we have other micro mega file, that is what's the name, that is 2 shape, which is showing a T wire technology. It is become highly flexible when we put the file into the canal, and when we take it out, it regain its shapes. It is high increased cyclic fatigue resistance and improved flexibility. But we don't know how it has been manufactured, but it is based on T-wire technology. Conclusion. So what we learn from this video, that is a file which is based on austenite phase. If it is austenite phase, its super elastic property is there. It shows more increased torque. So we can use this file system in which canals, which is straight and slightly curved. A file which has more of martensite phase means it is more flexible, increased resistance to cyclic fatigue. It can be used in complex curvature and anatomies. It can be used in severely curved canals, and we can pre-bend these files So we can use this file system in to bypass a ledge. So depending upon the case, if we're having a curved canals or if we're having a straight, because if we put a highly flexible file in a narrow constricted canals, we're not gaining something, because they are in a high constricted canals, we need more of torsional force, like torsional resistance. We don't need cyclic fatigue. But in highly curved canals, what we need is cyclic fatigue resistance. Cyclic fatigue resistance, it came from martensite phase, highly flexible phase. But torsional stresses, it came from austenite, which is more rigid. Even the path files, they are manufactured in austenite phase, because they are the first file that we need to put into the canal. We need that file to be more strong. So I hope we learned something new, or we have gained something. I try to describe all the things, but how the files are manufactured and what are the advantages and disadvantages about other file systems. So in my next video, I'll be telling in detail the structure of a file and what are the motions incorporated into the file. Thank you.